Okay, let's get started and talk about calculus. So it's been a while, so let's just like ease back into it. So what we're broadly doing right now is we're looking at the derivative and then later today the second derivative and trying to see what that tells us about the shape of a graph. And in the end, what you'll be able to do is just like given a function, you'll be able to sketch just like from scratch a little picture of it, which is kind of cool. And it'll be like at a pretty good level of detail as well. So here's what we know already. So this is like a reminder of stuff that we already did. So we had something called the increasing decreasing test, which is where we left off last time. And I feel like this one's pretty intuitive. So it just says if the derivative is positive, then your function is increasing there. And if it's negative, then you're decreasing there. So if f prime of x is greater than 0 on some interval a, b, then the function f is increasing on AB. So what this means is that given C less than D in that interval, f of C is going to be less than f of D. So as you take larger and larger inputs, the value of the function is getting larger and larger. Okay, and then the other side of this is if f prime of x is less than 0 on some interval a to b, then f is decreasing on AB. And so this is like the opposite. So if we're given some C and some D, where D is bigger than C, then the value of the function is going to decrease. So f of C is larger than f of D. And okay, does this make sense? Other questions about this? So the other sort of like information that we have about what the derivative of a function says about what the graph of the function looks like is sort of stuff about critical numbers. So in some sense, this is like the rest of the cases, right? What can the derivative be? It could be positive, it could be negative, it could be 0, or it could not exist. So if f prime of x equals 0 or does not exist, then that value is a critical number and you could have a local max or min there. So f prime, or sorry, this is a critical number. And there could be a local max or min there. So it doesn't have to be the case that you have a local max or min there, but it could be the case that you have that. So maybe I'll just draw some pictures to sort of illustrate. So here's one where the derivative is 0 somewhere and you have a local max. Here's one where it does not exist and you have a local max. Okay, but then you could also have the derivative be 0, but then there's no local max. So f prime is 0, no local max or min. And then one where the derivative doesn't exist. It would be something like that. So f prime of x dne, no local max or min. Okay, so really anything can happen here, but what you do know is that all of the local maxes or mins will have either the derivative is 0 there or the derivative does not exist. So if you want to find all of your local maxes or mins, you just need to find all of the places where this is true, and then check, which of these places. Okay, are there questions? This is kind of like recap from where we were at before spring break. Okay, so here's something new, but is maybe also pretty intuitive from what's written here. So this is called the first derivative test. And it says the following. So let's suppose C is a critical number. Of f, where f is continuous. Okay, so then what this is going to tell you is if your derivative changes from positive or to negative or from negative to positive at C, what happens? So then there's sort of 3 parts to this. So part A says if f prime changes from being positive to negative at C, so you're looking at f prime, and to the left of C, it's positive, and to the right of C, it's negative, then, so what should the conclusion be? So just think about this. The derivative changes from being positive to being negative at a point. What can we say about the point? So if the derivative is positive, the function is increasing. So it's like, and then if it's negative, it's decreasing. So it changes from being positive to negative at a point. Yeah. Yeah, so then that point has to be a local max. So then f has a local max at C. So here's just like the picture to remember is like you're increasing and then you're decreasing. So at, that point where you switch from increasing to decreasing, you have to be a local max. Yeah. The derivative is 0, but of the function. Yeah, so okay, yeah, maybe I'll draw both pictures. So okay, I'm gonna erase this. So let's say this is our f prime. So it's gonna change from being positive to negative. So I'll just draw it as like a line. Okay, so if f prime goes from positive to negative at C, you're absolutely right. The f prime of C is going to be 0. But then what will f look like? So it's going to have like for values over here, it has like a pretty large but positive slope. So something like this, but then at C, it has 0 slope, and then after that, it has negative slope. Making sense. Okay, yeah, I feel like this is the kind of thing where like, if you forget the statement of this, you can kind of logic it out by drawing pictures and thinking about what the hypotheses are saying. So then, okay, what is part B? Okay, so part B says it's the opposite. So if f prime changes from negative to positive at C, then, okay, now what's happening? Yeah, so then you're gonna have a local minimum at C. And I'll draw a picture again. So if our f prime, so now it has to change from negative to positive at C, something like that. Then our f could look like something like this. Then the last case is if it is either both positive, so the derivative is positive on both sides of C, or it's negative on both sides of C, then there's no conclusion to be made, unfortunately. So if it is plus plus or minus minus, so same, let me write a better statement. So if f prime of x is positive on both sides of C, or negative on both sides of C, then there's no local max or min at C. Okay, so here's how something like that might look. So C is a critical number, so that means that the derivative is either 0 or doesn't exist. So it could look something like that. So here you do have like that horizontal tangent, but we are increasing on both sides. So this is my f. And then what does my f prime look like? Might be something like this. I'm just trying to make sure that what I draw is like accurate to the, oh no, it should be 0 at C. So hold on. Okay, so okay, does that make sense? So here we have the derivative is positive on both sides of C, and so we get no local max or min. Okay, so we're gonna do an example where we sort of like combine all of the information that we have so far to analyze a function. But are there questions before we do that about the statement of this or anything else? Yeah.
Yeah, so if you're kind of wondering if the derivative is positive or negative, I mean, 2 points, I guess. Microsoft 2 points. It sort of seemed like most of the way you're supposed to do it is you just like pick any number that's between the two of them. Like, I guess you say something about like why that, like, and why it's okay to do that, to sort of assume the number you pick between 2 points.
Yeah, so like if so say you found where the derivative is 0 or where it doesn't exist, that breaks up the real line into intervals. So like, let's say, so here's the real line, and let's say you found that the derivative is 0 at like these 3 places. That's the only place where it can cross the x-axis. So if you test a single number from inside of one of those intervals, that will tell you whether the function is positive or negative on that interval for like the whole interval.
So it matters that those points have to be clear.
Yeah, yeah. But yeah, you would have to test something from each of these intervals. And yeah, we'll do also in the example, I'm going to give you another method as well, but plugging in like one number from inside the interval is reasonable. Other questions? Okay, so let's do the example. Okay, so we're gonna find where this function is increasing, decreasing, and we'll find the local maxima and minima as well for this function. So we're gonna find where it's increasing, decreasing, and we'll find the local maxes and mins. So the first thing that we're going to want to do is take the derivative and find where it's 0. That'll give us those critical numbers where so that'll break the real line up into intervals just like that, where on the interval, the derivative is either increasing or decreasing on the whole interval. And then those are also our candidates for being local maxes or mins. So let's do that first. So step 1, we'll find f prime of x. Okay, so this is just taking the derivative of a polynomial. So we get 12x cubed minus 12x squared minus 24x. Okay, and if you can eyeball a way to factor this, that's often helpful. For one, it'll tell us where this thing is 0, and then also that will be helpful when we're figuring out where it's increasing and decreasing as well. So I'm going to go ahead and factor this. So I can take out, easily I can take out a 12x, right? So we're left with x squared minus x minus 2. Okay, and then what about the second part? Does that factor further? Yeah, so we can do x minus 2. And then what's the other factor? Yeah. Okay, good. So then here's our candidates for the critical numbers. So find where f prime of x equals 0. Okay, so we can just, now that we have this factor, we can just eyeball where this is 0. So it'll be when any one of these factors is 0. So this could be, so if x is 0, then this will be 0. If x is 2, then everything will be 0. And if x is minus 1, then this will be 0. So we get f prime of x is 0 at 0, 2, and minus 1. Okay, is this making sense so far? Okay, so then let's figure out where f is increasing or decreasing. So by the like rules and tests that we have, this is gonna be whenever f prime is positive or negative. Okay, so we can draw this picture of the real number line, and we have, let's say, -1 here, 0, and 2. So f prime is 0 at these 3 places, and it's continuous everywhere else. So that means that on this whole interval, it could only either be positive or negative. Here, it's either positive or negative, and same thing here, positive or negative, and here as well. And so, like we said before, you could just test numbers from within that interval, but I'll show you another way that you can figure this out. So you can make this little chart. So we have 4 intervals to test. So we have -infinity to -1. We have -1 to 0, 0 to 2, and 2 to infinity. And what you can do, we have these factors in f prime. And so you can just decide on each interval individually whether like this is positive or negative, this is positive or negative, this is positive or negative, and then just count up the number of positives and negatives you have to discover whether the whole thing is positive or negative. So here's how like the chart method works. So here's our 4 intervals and then our factors. So we have 12x, x minus 2, and x plus 1. And then in this chart, I'll just fill in whether each of these factors is positive or negative on that interval. And then we'll get an overall determination of whether f prime is positive or negative. Okay, so for example, for numbers coming from the interval -infinity to -1, is 12x positive or negative? Yeah, it's going to be negative, right? So I'll just put in a minus sign into that box. Okay, what about x minus 2? Is that positive or negative on this interval? Yeah, this will be negative as well. And what about x plus 1. Yeah, that's also negative. Okay, so then in f prime of x, we're going to be multiplying 3 negative numbers together. So overall, it's negative on that interval. Okay, what changes on this interval? The interval from -1 to 0. What is this guy? Yeah, negative. What about this one? Yeah, and then this. Yeah, now this one's positive, right? Because we have, we're taking something from -1 to 0 and adding 1 to it. So adding 1 will push it positive. So now we get, so we have negative, negative, positive. So then what is f prime overall? Positive, yeah. Okay, so what about this next one? What is this one? Yeah, that's positive. I feel like, oh yeah, okay, so this is positive. What about this one? Negative and positive. I think I didn't put these in the best order, but that's okay. So this is positive, negative, and positive. So then overall f prime is negative. And then what about the last row? Yeah, those guys are all positive. Okay, so what can we conclude from this? So from this column, we can conclude whether f is increasing or decreasing on an interval, right? So here we get f is decreasing, increasing, decreasing, and increasing. Okay, and then from the first derivative test, we can also decide whether -1, 0, and 2 were local maxes or mins. So was -1 a local max or a local min, or neither? And why?
Switches from decreasing to increasing.
Yeah. Yeah, so the function is like decreasing, and then after that it's increasing, so you have a local min there. So let me write first derivative test. So we get that -1, this is a local min. What about at 0? We switch from, so here's 0, we switch from positive to negative there. So what is that? Yeah, we get a local max there. And then at 2, we're again decreasing to increasing, so we get a local min. Okay, so let me just like summarize the information. So f is decreasing on the intervals -∞ to -1 and 0 to 2. F is increasing on -1 to 0 and 2 to infinity. And then f has local mins at -1 and 2, and f has a local max at 0. Okay, does that make sense? Other questions? Okay, so that sort of summarizes like what the derivative tells us about a graph of f. So now we're going to add another layer and look into the second derivative to see what that says about f. And this is where I feel like it can get confusing because we're going to apply like the information that we know about the relationship between f and f prime, and we're going to like switch that to what can we say about the relationship between f prime and f double prime. Okay, so what does f double prime say about f? Okay, so here's two pictures I want you to see. So I'm going to draw two graphs of an f. So here's one, and here's the other one. So these two f's are both increasing on this interval, right? But they sort of bend in different directions. And this is the information that we'll be able to detect from the second derivative. So let's just look at the tangents of these. So here, let me not use purple because it's hard to see. So here I start off with something with slope like 0, and then small positive slope, and then like large positive slope, right? And here I have the other situation where I start with kind of a large slope, and then as I go along, I have smaller and smaller slope. So in this picture, the slopes are increasing. And in this picture, the slopes are decreasing. So let's just translate that information. So if the slopes are increasing, that means that f prime is increasing, right? Because f prime is a function that tells me what the slope is at a point. So if the slopes are increasing, f prime is increasing. And same thing for the other picture. We have the slopes are decreasing, so that means that f prime is decreasing. Okay, what does this say about f double prime? So if I have an increasing function, yeah, its derivative has to be positive, right? So this means that f double prime is positive. And here I have the opposite thing, so f double prime is negative. Does this make sense? Okay, so we're gonna give names to these two things. So this is gonna be called concave upward, and this is concave downward. Okay, so let me give you a definition for these two terms. And then I'll say, write out this, like what we just figured out here as more of a test. So here's the definition. For concave upward and concave downward. So if a graph is above all of its tangents on an interval, then it is concave upward on that interval. Okay, so let's just take a look at the picture. So here's the graph of the function and then each of its tangents. And you can see like the graph does lie above the graph of its tangents at every point. So that's when we say it's concave upward. And then the opposite situation, so when the graph is below all of its tangents on an interval, that's going to be concave downward. So if a graph is below all of its tangents on an interval, then it is concave downward on that interval. Okay, one last piece to this definition is going to be when points, so the points where the function changes from being concave up to being concave down, and that's called an inflection point. So a point P is called an inflection point if the curve or if the graph changes from concave up to concave down or vice versa at the point P. Okay, are there questions about the definition before we do examples? Okay, so I'm just gonna draw a crazy graph and then we'll just label where it's concave up, concave down, and what the inflection points are. So here's the graph of a function. Oops, I'm gonna do a different color. I don't think I quite passed the vertical line test here. Let me fix this. Okay, so let me make a little bit more room. So I want you guys to find where this is concave up, concave down, and the inflection points, and I'll give you like a minute or two to think about it. Okay, let's discuss. So I'm just gonna like scan across this graph and just yell now when there's an inflection point, okay? So I'll just, I'll go slowly. Yeah, so there's like something going on right here, right? We change, one direction or the other, okay. Something there too. Obviously, this isn't precise because it's just like a graph that I sketched, but yeah, something there. Yeah, so here we're changing, right, and then continuing. Oh, yeah, nothing for the rest of it. So let me label those inflection points and then, okay, so we had one like here-ish and then one maybe there and this guy. Okay, so on these intervals, let me just number them. Let's say this is 1, 2, 3, 4. Which ones are concave up? Yeah, so 2 and 4, we have concave up. And then what about 1 and 3? So what's going on here? So here we have concave down. What's going on at this point? I think this is like a little bit weird. So the definition for concave up was we want the graph to be lying above its tangent at that point. But here we don't have a tangent. So I think there we don't have a determination about whether it's concave up or not. So let's say like you're concave up on the open interval from here to here, and then again from here to infinity, but there's like no determination right there.
You read it the second derivative.
Yeah, yeah. The first derivative is also not defined there. Yeah, so you won't have the second derivative defined either. So this is not CU or CD. Okay, good. So I'm gonna summarize the observations that we're making earlier about what the concavity tells us about F double prime now and I'll phrase it as like a test. So this is called the concavity test. So this says that if F double prime of X is greater than 0 on an interval, then what should the conclusion be? It's going to say something about the concavity. Yeah, so we'll be concave up here. And then the part B is the opposite. So if F double prime of X is negative on the interval, then the graph is concave down. on the interval. Are there questions about this? Okay, so I'm gonna give you one more test, and this comes from the concavity test, and this is gonna be about whether your function has local mins or maxes at a certain value based on the concavity. So this is called the second derivative test. So this says there's two parts. If f prime of c is 0, so you have a critical point at c, and f double prime of c is positive, then, so what is the situation? We have a critical point, so it could be a local max or min, and I know that the graph is concave up there. So that means that C has to be a local min. And then the other half of this is that if f prime of C is 0 and we're concave down at C, then you have a local max at C. I think with these things, it's like really helpful to picture in your mind an example of something that satisfies these hypotheses, and then you won't get these conclusions mixed up. So yeah, you're like, so your derivative is 0, so you have a horizontal tangent there, and you're concave down, then that's gotta be it. Okay, so next time, we will combine all of these facts and we'll start sketching pictures of graphs. So I'll see you on Wednesday.